Hi, I'm Thomas Finn, and in this talk I will discuss joint work with Alexander Stauffer about multiscale techniques to analyze random processes out of equilibrium and establish coexistence in competing first passage percolation. As a brief introduction, multiscale techniques have arisen as a powerful and robust method to analyze interacting particle systems and processes like random interlacements. These methods usually rely on the system being in equilibrium and monotone, and we present a refined approach to handle models without these properties. The title of the talk is the same as our paper on arXiv if you do want to find out more. The model of interest in this talk is first passage percolation in a hostile environment, or just FPPHE, which is a competition model introduced by Sidovicius and Stauffer. It's a random competition model on ZD between two first passage percolation processes, FPP1 and FPP lambda. We can consider it on other graphs, but for this talk we won't. At time 0, the origin is occupied by FPP1, and FPP lambda is dormant in seeds that are distributed according to a product of Bernoulli measures of parameter p on the remaining sites. So this picture on the right illustrates this at time 0, so the blue circle is FPP1 at the origin, and the red circles are the seeds for FPP lambda. So FPP1 then spreads at rate 1, meaning it traverses an edge after waiting an exponential time of rate 1. So after a certain time, the model might look like this, where FPP1 occupies this blue region. Once a seed is attempted to be occupied by either FPP1 or FPP lambda, it is activated, and then spreads at rate lambda. So here, we might activate this seed, which then is occupied by FPP lambda, given by the orange process, and then that spreads at rate lambda to the edges of ZD, and it might occupy this site that neighbours it soon after. Once a site is occupied by either process, it remains occupied by that process henceforth. So if we run this for a bit longer, this portion of Z2 might look like this. So we're interested in understanding what this model looks like if we run it for a long time. What's the geometry of sites occupied by FPP1 and FPP lambda? So an important event in this regard is survival. So survival is if in the limit as time goes to infinity, there's an infinite connected component of a type. If that occurs, we say that type survives. This is the most natural definition for this, as FPP lambda will always occupy infinitely many sites, but it might not occupy an infinite connected component of sites. And if both processes survive simultaneously, we say they coexist, or there's coexistence. And we want to establish when can coexistence occur in this model. But there's two major difficulties we have to overcome. The first is that FPPHE has non-equilibrium dynamics. This is quite apparent from how we've defined the model, but something that's less clear is that the model is not monotone. And to see this, there's an illustration in the bottom right. So in this picture, we've added a single seed to a configuration, the small orange ball, that by doing this delays the activation of a large component of seeds. So by adding the seed, we might delay the large component of seeds being activated, and in this delay, FPP1 can encapsulate the large component of seeds. So we have a scenario where adding a seed can actually benefit FPP1. So this is a cute feature of the model, but it actually makes it incredibly difficult to analyze them. Models that are not monotone can have quite strange behavior. So how can we analyze this model? So before we discuss that, I'll show you some simulations of what FPPHE might look like. And just so we don't forget the dynamics, I'll put the dynamics down there going forward. Okay, so in this picture, we have FPPHE with a small density of seeds and a reasonably large lambda, but it's still less than 1. So the coloured region is sites occupied by FPP1, and the colour represents the time of occupation. The white region is a region occupied by FPP lambda, and grey is unoccupied sites. So there's an intriguing self-similar behaviour that we see from FPP1, and it's not clear at all what will happen if we run the simulation longer, whether FPP1 or FPP lambda survives. Well, one of them has to survive, but we don't know which one, and we don't know if both can survive simultaneously in this picture. So this highlights the intriguing behavior FPPHE can observe. And in this next picture, we have a large density of sites with p equals 0.4, but a minuscule lambda. So now, FPP1 must navigate around large components of seeds, but can spread typically well before FPP lambda propagates. So we see a significantly different behavior in this picture, but similarly, we can't really tell just by looking at it what we should expect to see. Should FPP1 or FPP lambda survive in this scenario? So now let's discuss some results for FPPHE. So the first result was by Sidovicius and Stauffer when they introduced the model. They proved in all dimensions greater than 1, for all lambda less than 1, so long as p is sufficiently small, then FPP1 survives and FPP lambda dies out with positive probability. Recall, this means that all connected components of FPP lambda are bounded. So note that this event can't occur almost surely, as the event all neighbours of the origin are seeds occurs with positive probability. So positive probability is, in a sense, a very strong statement for this model. So next, we prove that in all dimensions greater than 1, if p is smaller than 1 minus the critical probability for site percolation on ZD, so long as lambda is sufficiently small, then FPP1 occupies a positive density of sites with positive probability. The first thing to note is that if p is greater than 1 minus PC site, then it's easy to check that FPP1 will die out almost surely. So in a sense, our theorem is as strong as possible for the choice of p. Secondly, we don't just prove that it survives, which could be shown by showing that there's a path to infinity that FPP1 occupies, but actually FPP1 occupies a positive density of the lattice. And thirdly, our statement doesn't say anything about FPP lambda. So, then in our corollary, we can prove in dimensions greater than 2, if p is chosen between PC site and 1 minus PC site, and lambda is sufficiently small, then there must be coexistence. This is because the seeds percolate and there's an infinite connected component of them. And we can't deduce this in dimension 2 because PC site is greater than a half in that case. But in dimension 3 we know it's less than a half. So we deduce coexistence essentially from our main theorem. So how do we prove this? How do we prove that FPP1 can occupy a positive density of sites? So the proof is quite involved, but I'll present the main ideas now and the technique that we refer to as multiscale analysis with non-equilibrium feedback. So we want to show that FPP1 spreads well, and it will occupy lots of sites on the lattice, and it will survive and do this. So you can define good boxes locally in such a way that so long as FPP1 gets to the box first, then FPP1 will occupy most of that box. This isn't too hard to do. But the difficult part is guaranteeing that FPP1 arrives first, because this is not local information. I will need global information to deduce if FPP1 occupies lots of a good box. Because if FPP lambda gets there first, it doesn't matter how good the box is, because FPP1 didn't get there in time. So this is essentially why analysing non-equilibrium models is so difficult, because I need to incorporate non-local information. The idea is to define good boxes as having positive feedback if FPP1 arrives first, and negative feedback otherwise. In this framework, we can show positive feedback spreads well through good boxes, and negative feedback can only spread from bad boxes. And then, if we can show that the effect of bad boxes, i.e. negative feedback, can be encapsulated, then in a sense most boxes will have positive feedback, i.e. good boxes where FPP1 arrived first and can take advantage of the good local event. we must overcome the fact that there's arbitrarily large regions of bad boxes, which is why we need to do a multi-scale argument and control large regions of bad boxes at all scales. So this is done in this illustration above to give you an idea that at scale 1 we have boxes that are defined with local events just regarding the sites and the passage times to see if FBP1 occupies lots of sites there. At higher scales, we control the geometry of boxes at the lower scale immediately next. So the red boxes are the bad boxes at that scale, and the purple boxes are negative feedback. So as long as the bad boxes are well spread out, we can encapsulate the effect of negative feedback. And to control bad boxes at scale k, when we can't encapsulate it, then we have to go to a higher scale. So it's an involved argument, but this is the philosophy of this approach. And just as a final comment, recently Darvin and Sly have utilized similar techniques to analyze a spread of infection model that's very difficult because it's not equilibrium and non-monotone. So if you enjoyed this talk, I suggest you check out their paper because they have some very nice results. So thank you for listening, and if you want to discuss more with me, then please do get in touch. Thank you.